We don't really get lost in the forest that often, but we do have a lot of problems where we need to find a way out, and not just the way out, but the shortest way out. And boy, do we have a data structure for it. Welcome to the world of graphs. Unlike the trees that we've seen in the previous video, graphs do not have that many strict rules. In fact, graphs are pure chaos, but it also means that they open the world of possibilities. In this video, we're going to see what graphs are, how are they composed, which rules define them, spoiler, not a lot, and what we can do with graphs. So, what defines a graph? A graph is basically a set of nodes or set of objects. Let's say that we have cities as objects. In a graph, it's called nodes or vertices. We can have multiple nodes in a graph. In our case, it means two cities, and these two cities can be connected by a road. We can add more cities to the graph and also connect them however we want. As you can see, all three cities are connected to each other, which creates a cyclic dependency, which is not allowed in the tree, but it's a pretty normal thing to have in a graph. This graph is connected, which means that all objects have relations to each other. If we add another city, but we don't build a road, this city will not be connected to the rest of the graph, but it would still be a valid graph. But let's connect it for our purposes. The road can also go one direction or both directions. And if we want to specify this, the graph becomes a directed graph. We can represent it with arrows. Now it means that we can only get from this city to this city, but not back. Another cool feature of a graph is weight. In terms of cities, you can think about it as distance. For example, the distance from this city to this city would be 20 kilometers. And the direction from this city to this city would be 10. Not only you can see the distances between two cities, but you can also calculate the length of a path from this city to this one, which would be 20 plus 10. When we talk about graphs in a more mathematical notation, we call our nodes vertices, and usually you see them represented by a V. And the connections are called edges, and you see them represented by a letter E. It's hard to say what's not a graph because graphs are just a set of connected objects and anything can be described like this. But there are things that are not a graph. For example, a bar graph is not a graph, or a mathematical graph is also not a graph. And a graph of a function is not a graph in computer science. Unsurprisingly, this is also a graph. It's called a bipartite graph, which means that all the nodes in one part are connected to all of the nodes in another part. This is a node in real life. You can see the directions on it, which would be the neighbors, and you can see the distance to a point, which would be the weight. And this is something you really want to have when you're lost in the forest. There are so many ways to represent graphs in the code. The easiest one would be to use a map or a dictionary. In this case, the key is the node, and the values are the edges to other nodes. You can also create a weighted graph in the same manner, just by adding weights to the edges. But more stuff you add to your graph, more complicated the structure becomes. Another way that is amazing for graphs that are densely connected with each other is an adjacency matrix. And in this case, we have this 2D array where 1 is indication of a connection from one node to another node. You can imagine that's quite an ordeal to store though. Another nice and compact way is to store the edges of the graph without even establishing the nodes, but checking the adjacency of the vertices can be quite slow. You can even store your graph as a class if you need to store a lot of attributes and metadata, but it can get quite verbose quite quickly. Although I have to say, in the real code, when we work with real business object, this is quite common. Yeah, and how exactly is it going to help me get out of the forest? That's fair. Just knowing that graphs exist will not help you get out of the forest. But what if you knew how to find the shortest path? In the video about trees, we looked at the depth first search and the breadth first search, and the same algorithm applies for graphs, obviously, because trees are just a subset of graphs, which means that every tree is a graph, but not every graph is a tree. We can easily apply depth first search on a graph, but you probably wouldn't do that if you are lost in the forest. The breadth first search is a very useful algorithm because it's going to help us find the shortest path in a graph, given that a graph is not weighted or directional or have cycles. So how do we use breadth first search for finding the shortest path? Well, if you're lost in the forest and you need to call your friends to ask how to get out of the forest, you can try to apply this algorithm. Imagine this is you and this is your friend. And let's give you a little bit more friends to make it more realistic, hopefully. And let's say your friends also have friends that do not like you for some reason, so you're not friends with them. We want to say that one of these people knows how to get out of the forest. So first thing that you're gonna do, you're gonna call all of the friends that are your friends. So your first level of friendship. If one of them knows how to get out of the forest, well, you're done. And if not, you're gonna ask them for a list of their friends. And you're gonna queue all of their friends to ask them later. So when you call this friend, you're gonna add this one to the queue. And when you call this friend, you're gonna add these two. The queue in programming is absolutely the same as the queue in real life. First in, first out. Once you're done asking all of your friends in your first level of friendship, you can move on to the queue of a friend of a friend. And as you can see, you're already executing the breadth first search. If one of them knows how to get out of the forest, you stop the search, and if not, well, no luck. Well, just in case you have no friends, we can take a look at the distances between objects, or in other words, the weights of the edges of the graph. What are you going to do in that case? Well, you're going to apply a Dijkstra algorithm. Imagine you're in city A and you want to get to city D, and the edges represent the roads with the distances between these cities. And of course, you want to get to the city D with the minimum amount of kilometers. As a human, it's pretty difficult to find the shortest path in this graph, and that's why we have a Dijkstra algorithm to help us. The core idea of Dijkstra is that we're going to start at some point, we're going to look at all of the connected nodes to that point, we're going to evaluate what is the shortest path to all of them, and then we're going to travel to all of the other nodes to recalculate the shortest path from their perspective. And in the end, we're going to get to the shortest path to each of the nodes. Or in this case, we're more interested in the shortest path from A to D. Let's represent it with a table. Each value in the table will represent the distance from point A to all other points. We're going to start with point A, and we're immediately going to mark it as visited. We do it so we don't revisit the same node multiple times, because as you can see, there are quite some cycles in this graph, and we do not want to waste our time visiting the same node over and over. And as you can see from point A, we can calculate the distances to all of the other nodes. It's going to be 6 to point B, 2 for point C, and 9 to point D. And of course, 0 to point A. If we didn't have this direct connection, it would have been an infinity, because we couldn't possibly predict it. After we're done with point A, we're going to move on to the point with the shortest path possible, which is C. Let's mark it as visited right away, and we're going to recalculate all of the distances to other nodes. We already spent at least 2 to get to this node, so the path to B will be 2 plus 3, which is 5, and it's less than 6, so we're going to take it as a new value. And the path to D will be 2 plus 8, which will be 10. And it's bigger than the previous value, so we're not actually going to record it. And with that, we're going to move on to the next node, which is B. Let's mark B as visited as well. We already calculated that we can get to point B in 5 kilometers, which is 2 plus 3. And this is the path that we're going to take. We're going to ignore that path with 6 kilometers because, well, it's bigger, so we don't care about it anymore. We're going to look at point D, which is the only node that's not visited yet, and we can see that we have 5 plus 1, and it gives us 6, which is, to be fair, less than 9, so we're going to write 6 as our final version. When we are done with this algorithm, we can see that we can get to point D in 6 steps. It does not give us the path right away, but it's pretty easy to get it. The only thing you have to do is to write down the previous node for each of the nodes. Let me share how the final table would look like. As you can see, the first column is just nodes, the second column is the shortest path to each of the nodes from point A, and the third column is the previous node that we visited to get to that shortest path. And we can easily reverse engineer it from there. From point D, we go to point B. From point B, we go to point C. And from point C, we go to point A. But you might think, isn't it stupid. If you're lost in the forest and you're looking for a direction where to go and you have kind of an idea where you need to be, it's kind of stupid to go to that city just because it's the closest if you need to go over there. And you can solve this problem using a Dijkstra with a twist. Or should I say Dijkstra with a star, you know, a star. Imagine this is your map of getting out of the forest and you want to get from this point to this point. If we're using Dijkstra, we would start with this node, but it's very obvious from this map that this node doesn't really lead to where we need to go. And these nodes will actually have a preference. But how do we explain it to the algorithm? Well, we add something called hint. If you look at the scientific representation of a star, you will often see this. Before using the Dijkstra algorithm, we basically had this part. Everything that we need to take into account was the weight on the edge. But now we are adding something else. And this something else is calculated very differently for every problem you have. Just think about it as the closer you get to the proper direction, the bigger the h becomes. In all of the previous examples, we used distances as the weight of the edge, but it doesn't have to be like this. We can also use resources. For example, it'll take you 2 ounces of water to get from point A to point C, or 4 ounces to get from point A to point B. But what if the road from point B to point C is actually a river and you don't spend your water to get from point C to point B or the other way around, but you can refill your water? In that case, you can have what is called a negative edge. So instead of putting 2 or 4 ounces that you need to spend, you just put minus 5 ounces because this is the capacity of your water bottle. And it's amazing because it shows how versatile graphs are, but it also gives us some more problems. If you try to apply a Dijkstra algorithm to that graph, you will soon see that it actually fails. For graphs with negative weights, algorithms like Dijkstra will not work because they already checked the node with the shortest path to it. The node is marked as visited and we cannot update it anymore. Luckily, there are some algorithms like Bellman-Ford that can treat that types of graphs. They are quite resource intensive, but in case you need them, here they are. Imagine a Santa that's making a list and checking it twice. Well, Bellman-Ford will check your graphs more times. In fact, it's going to check it almost the same number of times as the number of vertices you have. So I probably wouldn't recommend using it on a large graph. And that is just the tip of the iceberg of all of the problems that graphs can solve for us. Think about the very, very simple one. Imagine you have a graph of courses that you need to take with the prerequisites and the prerequisites for the prerequisites. And imagine you need to get to your end goal, the courses that you really want to take, in the shortest amount of time, obviously. And how do you even figure it out if the graph looks like something exploded over there? And let's be real, that's how most of them do look like. You use topological sort. By sorting which courses need to be taken first and which courses need to be taken later, you can see the full picture very clearly. It's even applicable for just real humans, not just programs. Or think about the minimum spanning tree problem. Imagine a computer network. You want to get from one computer to another computer in the minimum amount of time with the minimum latency, as we say, and you really don't want to have any cycles there so you don't get lost in the computer network. Or another network flow problem where we are trying to find the bottleneck, or in other words, edges with a little weight that basically stop the whole flow of information or resources in the whole system. There are multiple algorithms that are trying to solve these and a gazillion of other problems, and the only thing they have in common is they work with graphs. Learning how graphs work and learning the simplest algorithm will give you the foundation that's needed to solve a really complex problem. And trust me, that's worth the time you spend on it. In no universe possible do I remember or even understand, let's say, Prim's algorithm for the minimum spanning tree. But since I know the basics, I can read about it, have some kind of picture in my head, and at least understand how it can be applied to different sorts of problems. I think the time learning foundation's easily worth it. Well, that was it about the world of graphs. It was just a short overview, but I hope you enjoyed it and now you want to learn more about graphs. I hope you didn't get lost in the world of graphs because there is no shortest path to get out of that. And if this whole explanation is complete gibberish, don't forget to leave a comment because I'm trying to make more content for non-engineers and it's incredibly difficult to learn to translate these terms to a normal people language, and I would like some feedback on that. Subscribe to the channel if you want to see more videos like that, and I'll see you in the next one. It's funny how I just unlearn how to speak. I'm not gonna walk that much. Attempt number 23 of something that's not even in the script. It's such a brain freeze, like, I mean...
Is a cycle a sickle or not?
Sickle? What?
A sickle, C-Y-K-E-L.
I don't have my phone. So sickle is a cycle in Dutch?
Yes, but only the one for graphs.
Just because you guys invented things doesn't mean...
That's exactly how it works. Just because we invent things, we get to name things.
Graphs are purely chaos, and I forgot what I was talking about. I'm gonna walk a lot today.